Dear students, I welcome you for the today's lecture related to the controllers in the process control designing systems. Now controllers basically they are pneumatic controllers and electronic controllers. The pneumatic controllers they are used in the process industries a long back, say before 30 years or so. Now, all these pneumatic controllers, they're replaced by electronic controllers because our electronic systems are very much advanced nowadays and they're also cheap, easy to operate, easy to function, easy to maintain. All these are the different advantages. However, we cannot forget about the history of pneumatic controllers, the root of development of this uh, different types of controllers. We have already studied this controlling the temperature in a vessel. For that, we have used the different notations. Ti is your inlet temperature, B the measured value of the controlled variable. I want to maintain the temperature of this. So Tc is my controlled variable for which the B is the measured value. It sends the signal to a controller and the controller gives the signal pressure output to the final control element, that is your control valve, where M, that is your manipulated variable, is associated with this control valve. Depending on the position of this control valve, the opening position of the stem, that means it is how much the control valve that is opened. Depending on its opening, the steam input to the coils that will be controlled. So this is what our simple temperature controlling system is there, for which we can write the block diagram, for which in which the controller that is there, a control valve that is there, the process and the measuring element that is there. Out of this process, we have already discussed the different processes and its transfer function, right? Whether it's a first order process, second order process, or pure capacitive process. So the depending on the different processes, I am putting the transfer function here. Gp is my transfer function for the process. The process can have the different transfer, first order, second order, or pure capacitance element transfer functions. And this process can have the different load variables. That is, load variable is nothing but the non-controlled element of the system. Then there is a need to study this control valve, as well as there is a need to study this controller, also your measuring element. So we have simply talked about this process. Now one by one we are going to discuss about the controller, control valve, and the measuring elements. So measuring elements we will be studying in the last unit. In this unit we will be talking about the controller and the control valve. So the transfer function of a controller is your GC, for which we are going to discuss it in this lecture. For control valve, we will be studying it afterwards. But understanding this block diagram is very essential. Developing this block diagram is very essential. It should be understood by one and all. So, going into the details of this controller today. Now, this is the pneumatic controller. The same system whether you are using the coils or whether you are using the heat exchanger for maintaining the temperature. Now what is happening in this case, the hot process stream that is available and it is being provided it is to be cooled with the help of a cooling water, so that the control valve, through the control valve, the cooling water that goes into the heat exchanger, and the temperature of this hot process stream is to be reduced. That is, this is my process requirement. This is what the process that is there. So for this process, for a heat exchanger, what will be its transfer function? That we have already discussed. Then I'm going to measure this outlet temperature and going to give the signal to the controller. So this temperature, depending on its intensity of temperature, this burden helix that is going to be connected to a flapper nozzle arrangement. This is a baffle or nothing but a flapper, and this is a nozzle. This is a pneumatic controller which was used in old days. So it is called a baffle nozzle system that is there. So baffle and a nozzle, or a flapper and a nozzle that is there. Now this is your measured variable. I am measuring the temperature from here, and it sends the signal to this limb. Then there is a set point knob that is associated, and which can be increased or decreased, and it gives a signal through this limb. So there are two limbs. One is for the measured value and another is for the set point. That is what we are going to do it in a comparator. A set point R and B, that is the measured value. It is going to generate the E error. Similarly here also, depending on this set value and depending on this measured value, it generates a error E. So this error generated, that adjusts the position of a baffle, and there is a nozzle. Now this is the air supply. We'll see the another figure for this assembly itself. It is one and the same thing. Here the air compressor that is there, a air container which will provide you the steady flow, and this is your baffle and the nozzle arrangement, or a flapper and a nozzle arrangement. This is what the measured value, and this is the set point. From this it generates a error signal that is generated, and depending on this error signal, that means this flapper moves towards the nozzle or moves away from the nozzle. So this is the nozzle, and if I am going towards the nozzle, that means what will happen? The air which is going out from this nozzle, there will be a restriction because of this flapper. So as I am going to move the flapper towards the nozzle, the back pressure that will be developed in the nozzle, and this developed back pressure which is going to the control valve, pneumatic output signal to the control valve, this developed back pressure that goes to a control valve. So this is the simplest arrangement. Now in addition to that, there is a feedback bellow that is provided, which is associated with your gain, steady state gain. That is, Kc is large, steady state gain values are large, and steady state gain values are low, for which I can adjust this connecting rod, and depending on this adjustment, this bellow exerts the back pressure also in addition to the nozzle pressure, and you get, or the air back pressure that is going to a control valve. So in this case, this is your supply of the air that is from the compressor, and here no baffle arrangement that is shown. It is with a Kc values, the gain values, then the baffle arrangement that is provided. So this output signal is, output pressure is going to a control valve. and depending on this output position, that means your baffle is going to change its position towards the nozzle. When the baffle that comes towards the nozzle, that means I am restricting the outlet flow from the nozzle. As a result, there is a development of a back pressure. Pressure will be developed more, and this more developed pressure will be sending towards the control valve, and this control valve is operated with this pressure. Every time all your control valves, they are operated on the pressure, air pressure. Mostly it is air that is used. Sometimes it can be your hydraulic fluid that is also used, depending on the requirement, pressure requirements. So one has to decide, understand this flapper and nozzle arrangement, where the supply which is going out from this nozzle is deciding the amount of the pressure which will be supplied to a control valve. Now, if this temperature that is lower, that means lower depending on my set point, so that I have to reduce this water flow rate. Temperature is lower than the set point, a certain error that is generated. So this valve has to be, cooling water flow rate has to be reduced. So this valve has to be closed, and depending on this valve that is to be closed, so that the adjustment of the pressure that is done by this flapper and nozzle arrangement. Now in this case, where the one baffle that is provided, it is your proportional controller. Then one resistance that is also provided, that makes resistance, that is a valve which offers the resistance for the flow. This produces the proportional derivative controller, PD controller, and in addition to this feedback bellow, one another feed forward bellow that is also added into the system, so that you are making it the proportional and integral controller. And the third case, that is fourth case, that is proportional, derivative and integral controller. So there are four types of a controller that is available: a proportional controller, a proportional derivative controller, proportional integral controller, and proportional derivative and integral controller. So these pneumatic controllers, they are proportional controllers. They are provided with only one bellow. Then to make it a PD controller, I am going to add a resistance. Then to make a PI controller, I am going to add another bellow. This is nothing but your bellow. Bellow is what? To adjust, absorb the fluctuations in the pressure. If the pressure that is exerted, then bellow gets expanded. If pressure reduces, bellow gets contracted. That is what the function of a bellow that is there. So this is the feed backward bellow and feed forward bellows. Two bellows are used in your proportional integral controller. And in case of a fourth controller, that is proportional, derivative and integral controller, there are two bellows plus the resistance that will be also there. So this makes the complete pneumatic controller. But nowadays these pneumatic controllers, they are not being used. So it is the need to study the electronic controllers. So this is what the explanation towards the figure. Now the transfer function for controller, because in our system it is all talked about the block diagram. For this process we have already studied the first order, second order and pure capacitance element as our transfer functions. Now we are going to study the controller transfer function. So controller transfer function, there are four types of controller as we have discussed. So one by one transfer function we will see now. The proportional controller. Proportional controller, that is what? The proportional controller produces an output signal which is proportional to the error. That is what? It's a proportional. One is your error. That is what? The generated error is of concern. The transfer function is output upon the input. So this is the GC of a controller, and its output that is there, and there is a one input. What is there in the input for a controller? E, that is there for the input controller, and P, that is your pneumatic pressure. That is what we have discussed in the previous figure also. This is the E, the error generated from the comparator, or error generated from the difference between the set point and the measured value, E, which is equal to the R minus B. So this is the error, or in this case it is the epsilon that is represented. So the error generated that goes into the controller, and the controller provides the signal in terms of a pressure. This pressure is going towards the control valve and adjusts the position of the stem of a control valve, or adjusts the opening of the control valve. Because all your pneumatic control valves, they are operated by the pressure. Air pressure is the source to operate your pneumatic control valves, and that is why air pressure, and that is why the terminology pneumatic that is coming into the picture. So pneumatic control valve, that is pneumatically operated valves, automatically operated or controlled pneumatically, that is why they are called pneumatic control valves. So this pressure, that is your output, this is the generated output from your transfer from your controller. So P, the output pressure signal from the controller, Kc, the gain or the sensitivity, epsilon, the error, or E, which is nothing but the set point minus the measured variable, and PS is usually adjustable to obtain the required output. So the transfer function in the following parts are developed for the pneumatic controllers. For electronic controllers, the same equations are applicable by changing the P with the suitable representation of a signal. P, instead of P, it becomes I, or the voltage. I to P converters are there, I or the voltage in case of electronics. In the last class we have talked the voltage is in between 4 to 20 current is in between 4 to 20 milliamps and voltage in 3 to 15 volts. So the proportional controller Kc, that is the controller gain, that is proportionality constant. This controller gain can be adjusted to make the controller output changes as sensitive as desired to deviation in the error. So Kc, this controller gain that makes the changes in the output, that means you are making it a sensitive, more sensitive to its functions, and depending on its sensitivity or the controller gain, you are going to manipulate the error. So when you are in the industry, you are going to play with this value of the Kc depending on your equipment. The signs can be chosen to make the controller output increase or decrease as the error signal increases or decreases. So it is usually adjusted after the controller has been installed. So the PT, which is the controlled output, controlled pressure, and epsilon Et, that is the error E, the controller GC, and your output is the P. So this pressure is directly proportional to the generated error. So pressure is directly proportional to the generated error and the proportionality constant, that is your Kc. This the controller gain. So your Ps upon epsilon s, which is equal to the Kc. So this is the transfer function for the proportional controller. The transfer function for the proportional controller is Gs, for which is equal to the Ps upon Es, which is equal to the Kc. This is related to the proportional controller. Now next is your proportional integral controller. Now what are the disadvantages? A steady error. Error is directly proportional to the pressure. So a steady state error occurs after the set point change or sustained disturbance is there. This can be eliminated by manually resetting either the set point or steady state value after an offset occurs. We will discuss it afterwards. So the proportional controller PI, it incorporates the proportional as well as the integral part. When you talk related to the integral part, that is the error, the for proportional controller PT is directly proportional to the ET. PT is directly proportional to the epsilon T or ET. This is for the proportional. And for integral, PT is proportional to the integral of the error, is proportional to the integral of ET dt. Integral is from 0 to t. So the two factors are there. One is the proportional and second is the integral part. So the output or the generated pressure, this is my transfer function in terms of a block diagram. This is output, which is the P, and this is the input, that is the E. So this output P is directly proportional to the E for the proportional part and is also proportional to the integral part in case of a integral controller. So that is why adding both the things, et dt, this is your integral part and this is your proportional part. So putting the proportionality constant, the Kc epsilon plus Kc upon tau epsilon dt plus Ps, where Ps is the constant set pressure. Now this Ti is your integral time. Ti is the integral time. So the term is proportional to the integral of the error and Ti is the integral time, integration constant. So PS, capital PS is what the output, which is equal to Kc. This is proportional term and this is the integral term. Kc taken out as the common and the output upon the input, that is what the transfer function is, Gc of the proportional integral controller, which is represented as Gc of Pi, or simply GPI. So transfer function for proportional integral controller is the PS upon ES, which is equal to Kc into bracket 1 plus 1 upon tau 1s. This is the transfer function for the controller with the Pi controller. Now the next is the PD controller, the proportional derivative controller. So the derivative action in terms of the dE dt. So your derivative term, that will be the Pt, that is proportional to the derivative of the error, is directly proportional to the d of error, derivative of the error, or epsilon. Epsilon and the E are the same, upon the dt. So this is the integral derivative part, and the proportional part is directly proportional to the error et. The error et. So pressure, output pressure is directly proportional to the error, and the output pressure is directly proportional to the differential of the error. So integrating this, you will get the Kc tau d dE upon dt. So this is your derivative part and this is your proportional part. is directly proportional to the E. E and epsilon are the one and the same thing. E which is equal to the epsilon. So Kc the gain, the tau d is the derivative time, this constant, that is the Kc tau d that is coming into the picture, which is the tau d is the derivative time. So this is the proportional derivative integral transfer function. So the derivative transfer function, I can write Kc epsilon plus Kc tau d into dE upon dt, which on simplification you will get Kc into bracket 1 plus tau ds. So this is the proportional derivative controller. Transfer function for proportional derivative controller is Kc into bracket 1 plus tau ds. Now the fourth type of a controller, that is your proportional derivative and integral controller. So this is incorporating the pressure, that is Pt is directly proportional to Pt is directly proportional to the number 1, that is the error Et, that is nothing but my derivative part. Then it is directly proportional to the differential of the error det upon dt, et upon the dt. And the third is integral of the error et dt. So it will depend on all the three factors: the proportional factor, the derivative factor, and the integral factor. So it is incorporating the proportional, derivative, and the integral. So your transfer function, that is the output deviation variable upon the input deviation variable, that is the P is your output. Output is your pressure, nothing but the pressure from the controller, or the current or voltage from the controller in case of electronics or pneumatic controller. Pneumatic controller may, it is the output is directly as a pressure going to the control valve. However, in the electronic controllers, we are providing the I to P converters, so that the I is your current and P is your pressure. Though current from the controller, that is being converted into the I to P converter into the pressure, means pressure uh, current from the controller that will go to the I to P converter, and this I to P, output of this I to P is your pressure. So this is related to the electronic controller. So the general transfer function is Kc 1 plus tau ds plus 1 upon tau is. The same, they are added. So all these are the different controllers. Now we will see it a graphical representation how they behave for a step change. If this is a step change, epsilon t is error which is considered to be the 1, and step change et, that is equal to the at. So after the application of this step change at, what deviations you will get, that is of more concern, and this analysis is of more importance, and depending on this analysis, how to select a controller becomes an important point. So one by one we will do the analysis. Now if this system, this is a deviation variable, deviation is from the difference between the set point and the controlled variable. Deviation is the difference between the set point and the controlled variable, or you can say the offset, variation from the desired value, deviation from the desired value. Desired value is your set point. So how much it is deviated. If no controller that is being used, then my behavior, output behavior will be like this. It is a deviation variable against the time. This graph is plotted. So continuously increases, and after that it attains steady state value, that is without a controller. But there is a vast difference between the required value. This is what a required value, this is what a set point, the x-axis is a set point, and the, you can say this is the C, that is the output, that is what our process overall. When you draw the overall process after reduction of the block diagram, after reduction of the block diagram, I am putting this as the R and putting this as the C. This is after reduction of the block diagram. Our basic block diagram which we have studied in the last class is this thing. Now after reduction of this block diagram into a single block, that is combining all the transfer function, my output will be this C upon R. So I am representing this in a one single block of the reduced flow diagram, where this is the value of R and this is the value of C, the controlled variable and the set point. So this is the basic block diagram which is to be remembered. And so if no controller that is used, then there is a lot of deviation, lot of offset. Offset, that is nothing but the difference in the magnitude of the set point, that is R, and the controlled variable C at steady state condition. At steady state condition means I am having the R value infinite, that is fixed R value, and C infinity, that is the controlled variable. So offset is the difference in the magnitude of the set point and the controlled variable. So this is what the offset, a big offset that will be obtained, big deviation, or this is nothing but the offset that will be generated. This is the offset that will be generated for no controller. Then there is a proportional controller that has been incorporated. So this proportional controller will have the oscillations, its response is oscillatory, and after a very long time it may attain a steady state value after the infinite time. Then there can be the proportional derivative controller also. So this is the graph for your proportional derivative controller, the same graph that is there. So there are less oscillations. Oscillations are less when you put a derivative action. Oscillations are reduced, but there is a offset that exists. This the offset that exists in case of the proportional as well as the proportional derivative controller. This is the offset that exists, and the offset for the proportional and proportional derivative controller is more or less same magnitude. So this is what we are discussing, the deviation of the controlled variable against the time factor. For no controller, there is a big deviation that is observed. Then for proportional controller, the deviation is there, offset is there with oscillations. However, when we incorporate the proportional derivative controller, the offset is there, but the oscillations are reduced. These oscillations, they are less in comparison with the proportional controller. Then the third is the proportional integral controller. In proportional integral, you can see the lot of oscillations are there. But the offset is 0. The required value matches with the desired value. That is your R infinity minus C infinity, that becomes equals to the 0. This is nothing but the offset. So this offset becomes 0 for proportional integral action. Then for the proportional integral and derivative, there is a reduction in the integral action that reduces the offset. Integral action that reduces the offset, but having the oscillations. इंटीग्रल एक्शन में ऑसिलेशंस है, बट डेविएशन नहीं है. However, in case of a derivative controller, there are less oscillations. Oscillations are damped, but there is an offset. So the proportional integral controller that reduces the offset as well as reduces the deviation, and that is why for better controlling you are going to use the proportional derivative and integral controller, where offset as well as the oscillations, they both are reduced. Oscillations as well as the deviations both are reduced. If the disturbance occurs the value of the controlled variable, that is without control, this variable continues to rise to a non-steady state. So this is all related to